Fine, good morning. So, kinematics are fluid, and in that, right, so you have to understand some of the basic concepts. So, one is field concept, and then the streamlines equation. And the third one is local convective and material derivatives. And then incompressibility, irrotational. So these are the basic concepts actually that you have to be aware to understand this particular topic. And here, the first is the field concept. So does anybody aware what is a field? What is a field? Anybody aware what is a field? So this is at multiple locations actually we will be dealing with this field concept. Suppose if you take electric field we mean, suppose if there is a charge here, and from this particular charge the electric field lines, which are nothing but the force lines. Suppose if I keep, let us say the charge of this particular charge is Q, and let us say you have kept 1 coulomb charge here, and then the force exerted on this particular 1 coulomb charge away, right? So this is the direction of the force, right? Suppose if I keep the same particle here, then it will exert the force in this direction. Suppose if I keep it here, it will exert in this direction. Now, whatever may be the place you put it, it will always be away from this particular center, right? So this particular lines, all these lines are imaginary force lines. Imaginary force lines, we mean these lines are not really drawn there. If you keep a charge, it will move in this direction. That is the assumption there. Got it? Understood or not? So all these lines together, if you represent with an equation called E of R, then this equation we call as electric field. Got it? Electric field. So here, exactly in the similar manner, if you take on the earth, whatever may be the body, if it is going a little bit high, then it will always be directed towards the ground. Suppose if this is the earth, then whether you keep the particle here, it will be drawn like this. So it will be dragged towards the ground always, wherever may be the position it is. Suppose if you keep the particle here, it will be attracted towards the ground like this. Now all these lines together, if you represent with some equation, and this is what we call as the gravitational field. So that means all are imaginary lines, and all these lines are always directed towards a specific, or these are moving in a specific direction. All the lines together we represent a single equation we call as the field. Got it or not? So usually we use the terminology flow field in case of fluid fields. Flow field. So here, imagine a flow is happening like this. Now, all these lines are nothing but these fluid particles are moving in a specific direction here. And then, if you take at any instant, there are certain movements like this. All these movements together, if you are able to represent with an equation called F of R, then this is the flow field. Got it? Understood or not? So these fields are usually the vectors. So vectors or field vector, we mean, suppose if F is equal to h of x comma y comma z into I plus g of x comma y comma z into j plus p of x comma y comma z into k. So this is how usually a field is represented. Got it or not? This is a generic field. It may be a gravitational field, or it may be an electric field, or it may be a fluid field. Understood or not? So this is the concept of field. The field, we mean there are certain lines which are drawn in a specific direction represented by these equations. All these lines together we represent with a single equation called field equation. Suppose if I say y is equal to x, then this is a single line. This is a single line. Suppose if I keep y is equal to mx and then m being variable. So now actually this represents a multiple lines. These multiple lines together we call as field. Got it or not? So this is only one direction, that's why mx. Suppose if it is happening in all the three different directions together, then we represent with a vector f. So all these together will represent the field lines in all the directions. Clear? Do you have any questions on the field concept? Any questions on the field? Okay, great. So you can note down this and then we'll go to the streamlines equation. Noted? Okay, great. Now, the second one is the streamlines concept. So the streamlines concept is nothing but represents the flow. Direction. So this represents the flow direction of the fluid. Now let us say if the fluid is traveling in a specific direction like this. So this is the summation of all the individual particles velocities together in a specific direction here. At any instant, if you take, so the tangent, if I draw it, this is the direction of the velocity. The tangent direction is the direction of the velocity. This is the direction of the velocity. And then on this line, if you take it, so this is ds, which is nothing but dx into I plus dy into j plus dz into k. So this is elemental change in the space. Now, let us say this fluid is traveling like this, and then at this instant the velocity direction is tangential to this particular point, right? Now, if this is the change in the ds is nothing but the space movement. From the x1, y1, z1 to, it changed to x2, y2, z2. That means there is a change in the value of x, change in the value of y, and there is a change in the value of z. All the three changes together, we will treat as a single vector. ds is equal to dx into I plus dy into j plus dz into k, or sometimes it is even represented with dr. So dr is equal to dx into I plus dy into j and dz into k. Now, if I wanted to derive the equation of motion, or if I wanted to derive the equation of the flow direction, right? So here the condition will be, as and when if I draw a tangent at any point, it has to be exactly matched with the ds direction. Correct or not? As ds tends to 0, if I draw a tangent, it will always have to match in the same direction. So that means ds cross q. Q is nothing but the velocity. Let us say let the velocity vector q is equal to ui plus vj plus wk. So this is the velocity vector, and the space vector dx into I plus dy into j plus dz into k. So this is the space vector. So at any instant, if I take it, the direction of both should be the same. Then only this, whatever the equation, I can get it from this, right? So this will represent the streamlines, or nothing but the flow direction. Got it or not? So these directions are same. That means the cross product will be vanishing. As the directions of q and ds are same, to represent a flow, then ds cross q should vanish. I hope you understood the meaning of this. ds cross q is equal to 0. Do you have any questions on this? So when the cross product will be 0? In a vector, when the cross product will be 0? Yeah, when the angle between them is 0. Here, this is the ds direction, and this is the velocity direction at one point. Now the cross product, if I take it, it will be 0. Suppose if I take it one more location here, this is the ds direction, and this is the velocity direction at that point. Again, at this particular instant, if you consider, both will be the same direction, right? So the wave flow is moving exactly in the similar manner. You will be drawing the tangent vector there. So finally, what our intention is, you wanted to identify the streamlines. Streamlines means the flow direction. So wherever the flow you wanted to identify, the cross product has to be vanished. Then only it will show the equation of the motion. So that is dx into I plus dy into j plus dz into k cross ui plus vj plus wk. This should vanish. Then I, j, k, dx, dy, dz, u, v, w. So this is the way we usually find the cross product. So this is I times of w into dy minus v into dz minus j times of w into dx minus u into dz plus k times of v dx minus u dy. Now this should be equal to 0. This will be equal to 0 only when all the individual components are equal to 0, because this is a vector, so you cannot mix up together. Each and every direction has to be treated separately. That means this component is equal to 0. So 0 into I plus 0 into j plus 0 into k. So this is how actually it will be equal to a null vector. So the correspondence, if you equate it, w dy minus v dz is equal to 0. It implies dy by v is equal to dz by w. So you note down this. So I'm going to write it. I think it's not visible. Note down till this point. I'm going to erase it. Done? Okay. So here v dy minus w dz, w dy minus v dz equal to 0. It implies dy by v is equal to dz by w. And the second one is w dx minus u dz. It implies dx by u is equal to dz by w. And the third one, v dx minus u dy equal to 0. It implies dx by u is equal to dy by v. Now all the equations together, if you write it, then it will be dx by u is equal to dy by v is equal to dz by w. So this is one of the very important equations which represents this equation represents the equation of the streamline. So this represents the equation of the streamline. Got it? So at multiple places we will be using this equation. You have to remember this. Then the local derivative, convective derivative and material derivatives. So what it means for us is, suppose let us say there is a fluid particle that is present here in the flow. So there is a flow that is happening. On that flow, randomly you have considered one fluid particle, and then let us say this is having a position vector of r from the fixed location. So this is the origin of consideration. So this is a coordinate system we are thinking of. So the position vector is represented as r. Now let us say after certain interval of time, so this particle is moved to this location for a distance of ds. Let us say the velocity of this fluid is q. Let the velocity is v. Sorry. Usually in our terminology of fluid dynamics, it is usually represented with a letter called q. So wherever q is there, then you can imagine that this is a three-dimensional velocity uv, so ui plus vj plus wk. So this is the way we represent the velocity vector in case of fluid dynamics. So this is the q. Then this q, velocity is equal to usually displacement by time, right? So that means ds is equal to q q into delta t. So this is the elemental change in the position of the particle from this location to this location in a time interval of delta t. Got it? So this is the ds. So this is the initial position vector. Then this is r plus ds. Right? R plus ds. Or actually you can even treat as r for convenience. R plus dr. Now at a later point of time, this particle is moved from this location to this location. Now during the meantime, let us take any random fluid property. So let us say if you take the q itself, random fluid property, F. For example, the velocity of the fluid itself is one particular property. The acceleration of the fluid is a property. Now, like that, if you take a random fluid property, so if you wanted to find out the derivative of this particular random fluid property from this location to this location, there are two changes that are going to happen in here. So one is at this particular point itself, if there is a change in the velocity itself, so here there will be a change with respect to time. There will be a change with respect to time at the same location after certain time, obviously, right? And then there is a movement from here to here. During this movement also, there will be a change in the fluid property. That means there are two changes that are happening from here to here with respect to the time. One specifically because of time and another is specifically due to the change in the position. Got it or not? This is very important to understand. So a fluid property can be changed with respect to time in two different ways. One is change with respect to time from there and change with respect to the positional change. So because of these two, the fluid property is going to be changed. Now this fluid property, if you want to find out the time derivative, the time derivative or rate of change of the fluid property can be completely described both with time and space. Both with time and space. Now, if you consider that, let us say initially the fluid property at this point, this is f of r comma delta t. R comma delta t is the initial fluid property at the position of the initial condition. So at this point. Now after certain time, this is moved to a different location. Then the function is going to be changed to r plus delta r. And then t plus delta t. So this is the new function. Got it or not? So the function at this particular point is f of r comma delta t, and the same function, right? So when it is moving to this particular location, so this is happening. One is positional change from here to here, and within that time there will be a time change. So that is f of r plus delta r and t plus delta t is the new function value at the position B. So this is position A. Got it? Then the change in the function in a time t, so in a time delta t will be delta f divided by delta t, right? So this is the time rate of change of the function f with respect to time. Now this with respect to time, this is happening, the change from f of r plus delta r comma t plus delta t minus f of r comma t. This is the way actually we tried proving Cauchy-Riemann equations, right? There actually we have used this kind of condition. Initially f of r comma t, it's not r comma delta t. Delta t is the change. Yeah, sorry. So r comma t. Got it? So here actually when we prove the Cauchy-Riemann equations, this kind of thing actually came into picture, right? So now here this is f of r plus delta r and t plus delta t minus f of r comma t. Now if you expand with the help of, so expand f of r plus delta r comma t plus delta t with the help of Taylor's expansion. With the help of Taylor's expansion. So can you note down till this point? Then it will be f of r comma t minus, plus dou f by dou r into delta r plus dou square f by dou r square into delta r whole square plus dash 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 up to infinite plus dou f by dou s. Okay, note down this first. So this part anyway I will rewrite it. Done? Now if we expand with the help of Taylor's expansion, f of r plus delta r comma t plus delta t can be written as f of r comma t plus dou f by dou r into delta r plus dou square f by dou r square into delta r whole square plus dash 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 up to infinite, and then plus dou f by dou t into delta t plus dou f by dou square f by dou t square into delta t whole square plus dash 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 infinite. Now f of r plus delta r t plus delta t divide with delta t and limit delta t tending to 0. Then this will be dou f by dou r into delta r, and then assume that delta r whole square onwards it is going to be 0, as delta r is nothing but delta r is equal to, from this equation, that will be q into delta t. So as delta t tending to 0, then delta r will also be 0. So this is delta r, then dou f by dou t into delta t. And the higher order terms you can neglect it. Higher order terms we can neglect as delta t tends to 0. Tends to 0. Now, this is nothing but df by dt. And this can be written as dou f by dou t into dt. Sorry, so this can be written as dou f by dou r into delta r can be written as q into delta t. Then this delta t, if you cancel it out, dou f by dou t plus dou f by dou r into q. Q into dou f by dou t. Got it? And this was, in short, it is written as dou by dou t plus q dot del of EF. Note down till this point. I am going to explain this. This is R. Done? Okay. Now see this equation, that is dou f by dou t plus q dot dou f by dou r is written as dou f by dou t plus q dot del of f. So these two are equivalent to each other. Here dou f by dou r, and here r is nothing but the vector xi plus yj plus zk. Now this is a vector. Now the derivative with respect to vector we call as del. With respect to space vector, we call as del. So del is defined as I dou by dou x plus j dou by dou y plus k dou by dou z. So this is a vector operator. So this is a vector operator. So this was in short written as q dot del. So q is as usual, it is coming from the equation, but dou f by dou r is treated as del f. Got it or not? Understood? So this is here actually, in short, whatever we have done till this point is, suppose if there is a fluid particle here and this particle is moved from here to here in a time interval of delta t, and then this fluid particle is associated with certain fluid properties, maybe density, maybe velocity, maybe acceleration or anything else. So these are the fluid properties that we are going to analyze it. Now, after a certain time, how this fluid particle property is going to be changed after a certain time is dependent on two different aspects. At this particular position itself, there might be a change of the fluid property there itself, even though whether it is moved or it's not moved. So there might be a change with respect to the time. Got it or not? So that means at that location, initial position itself, there might be a change with respect to the time itself. And then while moving from here to there will be a change in the property again. Just because of the movement, it has got some more ability or some more change in the fluid property. Now, essentially, if there is a time rate of change mean, there will be a change here and there will be a change because of the movement. These two together we call as the change of the fluid property. Got it or not? So that's why if you notice in this part is nothing but local derivative. Because this is the fluid function or the property is f. This f is changed from the same location with respect to time alone. And this is change with respect to space. So change because of the time and change because of the space. Together we call as, so this is called as the convective derivative. Convective derivative. This is what we call as the convective derivative. Now, these two derivatives together we call as df by dt. So here, if you notice, we use capital letter. Convective derivative. Sorry, for material derivative. Together we call as material derivative. Got it or not? So one is change because of the time itself, another is change because of the space. Now, if you want to consider the total change, it will be both together. Change because of the time itself, we call as the local derivative. Change with respect to the space, we call as the convective derivative. These two together, we name as the material derivative, or one more name, substantial derivative. Substantial derivative or material derivative. This material derivative is going to be used in some of the cases of fluid dynamics. So that's why we'll have to understand what is this material derivative. Clear? Any questions on this? Any questions? So this is the thing that you have to be aware. So the material derivative of any fluid property is nothing but dou f by dou t or dou by dou t plus q dot del times of f. Suppose if this f equal to q, then dq by dt is equal to dou q by dou t plus q dot del q. This is nothing but the acceleration. See, the acceleration. So if f becomes q, now actually you wanted to find out the derivative of q. Q is nothing but the velocity vector. The velocity vector, time derivative, if you take it, this is happening both because of the time and the space. So that's why dq by dt plus q dot del q. Understood? Any questions on this? So this is the thing that you need to remember. Note it down. Okay. And then incompressibility. So this concept you might be already aware, because in the vector calculus itself you might have learned that what is incompressibility. Suppose if there is a fluid and that fluid, let us say it was completely filled up in a box and the box is completely full, then if you wanted to push any extra water into the box, then automatically there will be a certain quantity of the fluid that is coming out. Why this is happening? Because the fluid is not compressible there. Now take one more example. If I take the same box and then I'll fill up with some sponge, and then now the box is completely full. Suppose if I put extra sponge into it and then press it, then automatically I will be able to accumulate that sponge into the box. Got it or not? Why I am able to push again and then keep extra sponge into the box? Why I am not able to push in case of fluid? Understood or not? I hope you understood my question. So in case of sponge, for the same box, I will be able to push some extra sponge into it, though it was completely filled. In case of fluid, if it is completely filled with the box, then if I push extra fluid, then some fluid will come out. It won't be accumulated there. What was the reason behind it? Any idea? So that's exactly the nature of compressibility. Suppose if you are able to compress it and put some extra, then there will be a certain quantity which needs to be associated with that. That is nothing but particle density is going to be changed, but the material should have the association of changeability of the density. So that property we call as the compressibility. Got it or not, Rishi? So compressibility, the ability to compress itself, right? So it's called compressibility. Mathematically, this is nothing but the fluid field or whatever may be the field it is. So there are all the directions, the changes are happening. Now here that is represented with del dot F is equal to 0, non-compressible. So if the F is representing a fluid field, then or whatever may be the field it is, and then del dot F is coming out to be 0, then it is incompressible, non-compressible or incompressible. Suppose if it is not equal to 0, then compressible or expandable. So depending upon the value, it may be a positive value or it may be a negative value. If it is 0, incompressible. If it is not 0, either expandable or compressible, depending upon the value of the del dot F. So this is the nature to test whether the function is compressible, so whether the field is compressible or not. Got it or not? Exactly in the similar manner, in case of irrotational nature, So why we are doing this way is, this is nothing but del dot F is equal to I dou by dou X plus J dou by dou Y plus K dou by dou Z dot F is nothing but, so some function Hi plus Gj plus Pk. Then this is, or I call this as Fx, Fy and Fz. Dou Fx by dou X plus dou Fy by dou Y plus dou Fz divided by dou Z. So this is del dot F. Now here if you notice the derivative with respect to X, with respect to Y and with respect to Z. Now all the three different directions there is a derivative exists. Now all the three derivatives together is coming as, we call as the change in overall function. This change is happening just because of the changes in the individual X, Y, Z directions. So this essentially means that the fluid property can be compressed or can be changed with respect to the space. This is what we call as the compressibility in mathematics format. Got it or not? Understood? So coming to the irrotational nature. So this irrotational nature, as I told you earlier, right? So in case of cross product, the perpendicular component of the force is coming into picture. So I have explained the concept of door for the cross product when I am taking the foundation classes. So here, if there is a so suppose if there is a door and this is a door and this is the position where we hold the door, and then if we apply the force with our hand, so you can drag like this or you can push like this. Now here when you are dragging or pushing, then the force that is applied is going to be exactly perpendicular to the door. Even if you apply in a cross manner like this, hold like this. So if you are applying the force in a cross manner like this, but the essential component of the force that is getting used to drag this door will be the perpendicular component of the force. Now if there is a perpendicular component of the force and for the radius, so this is the radius vector where I am applying the force, and though I am applying the force in a cross manner like this, the perpendicular component of the force will be exactly perpendicular to this door, and these two together will make the door to move in this direction, wherein the axis of rotation will be this one. Got it or not? Here this is one vector, R vector, and this vector, the force vector, F vector, and the R cross F is nothing but the torque. So this is the torque vector. So torque vector is having an axis of rotation. This is the axis of rotation. So this torque direction will be perpendicular to both. Right? Perpendicular to both. Now here, if tau has to be 0, then R and F should be exactly in the same direction. Now this particular force, if I drag in this way parallel to the door, then there won't be a movement or there won't be a rotation in this particular door, right? Got it or not? So if there is no rotation, then obviously R cross F will be equal to 0. Exactly in the similar manner, this is the physical objects actually which we can see and touch. So that's why actually you can feel that. So there won't be any rotation. But in case of fluid, right? So that will be continuously changing. Now you can see some curls in certain locations. So you can see a straightforward flow of the fluid in certain locations, right? Now to identify whether there is a circular rotation for any of the fluid at any instant, right? So you have to identify whether these force components are perpendicular at that location or not for the fluid flow. Now, if there is no circulation, then the way you can assure there is no circulation will be this value, that is del cross F should be equal to 0. Del cross F should be equal to 0. This is the condition for irrotational flow. So here, these are simple normal vectors. You can find it out. Now here, the changes in all the three different directions should be equal to 0, right? So that's why del cross F is equal to 0. This is the space derivative. That is I dou by dou x plus j dou by dou y plus k dou by dou z is the derivative that we are considering here. And cross F is nothing but 0. So del cross F value, if it is coming out to be 0, then you can conclude that the flow is irrotational there. Got it or not? So this you have learned already in vector calculus to verify whether the particular field is rotational or irrotational. Understood? Now here, this is one of the important aspects that we have to understand when we are dealing with the fluid dynamics. Here, this itself actually will divide fluid dynamics into two different kinds of analysis. One is this del cross F. If it is equal to 0, then F can be expressed as minus del phi. So this is one of the important property. That means del cross del F is always equal to 0, phi being the scalar. So this is a vector and this is a scalar. So the beauty here it is, F is a vector, phi is a scalar. So if del cross F equal to 0, then obviously these two has to be in the same direction. Then F is, if you can express minus del phi, where phi is a scalar field, then del cross F, del cross del phi will be definitely equal to 0 because both will have the same direction. Then, which essentially means that F can be expressed as minus del phi. So what is the advantage of expressing F is equal to minus del phi is, so phi is scalar. This is the only greatest advantage. Then this phi, in general physically, we call this as the potential. So the potential. So phi is a potential. So if you take the derivative with respect to the phi, so space derivative for the function phi, then what you are going to get is the fluid field F. So this is a vector. So this one divides the fluid flow analysis into two different ways. So this will give a convenient way of analyzing. Now, when there is a potential difference, suppose if I leave this chalk piece, it is going to go down, right? So why it is going down? Because there will be a potential energy difference from this location to this location. Obviously, at higher position, it will be having higher potential energy. At lower position, it will be having a lower potential energy. So from top to bottom, it is traveling just because there is a lower potential energy below to it. That means, if you notice, this chalk piece, if I leave it, it is exactly going in a straight line manner downwards, but it's not going this way like this. Got it or not? So here in this case, you can analyze as if like, if there is a potential difference between these two planes, obviously there will be a flow exactly perpendicular to these two planes. And this kind of flow we call as the potential flow. Why negative sign? Obviously you can notice from higher to lower only it is traveling, not from lower to higher. Got it or not? So that's why we treat as the negative. Negative means, so higher potential energy at this point, lower potential. Higher to lower it is traveling, right? So at the initial position number 1, it will be the higher value. At position number 2, it will be the lower value. So when you take the difference from lower to higher, that is the convention of taking. So if you take lower to higher, it will be a negative. So that's why minus of del phi we treat. And then this kind of flow analysis we call as the potential flow or potential energy flow. Here, in case of potential flow, these are equipotential planes, let us say, then flow will be exactly perpendicular to these planes. So this kind of flow we call as the potential flow, and this is the most easiest way of analyzing. Most easiest way of analysis, right? And then if there are curls, that means del cross F is not equal to 0, then you cannot express in this format. So if del cross F is not equal to 0, that means there are some rotational components of the fluid flow that will be there, right? So if there is a rotational component, obviously you cannot think of a equipotential planes, right? So you cannot use this potential flow analysis, or you cannot express as a scalar potential in case if there are curls that are present. That's why when you take any fluid flow that is happening in a river, then the water is suddenly flowing like this in a continuous manner, and then I'll just write here. I hope you noted down this. Let us say there is a dam here, and then fluid is coming from infinite location like this. But the moment it reaches the dam, right, here actually there will be certain curls like this. So you can notice that there will be a big hole that is at the middle point, and then the water is continuously rotated and going down, right? And then from here actually it will exit from the doors of the dam, right? Yeah. So here this is the flow. So laminar flow is a little bit different, that I am going to explain when I deal with the viscosity. And here actually the potential flow is just because of there is a potential difference. That's the reason why it is moving. So why the fluid has to travel in this direction? Why not in the opposite direction? So the fluid is traveling from here to here, but it's not from here to here. The reason being, here it is having the higher potential energy, here it is having the lower potential energy. So this is the equipotential planes. Now the fluid will go exactly perpendicular to these planes like this. Now the moment it comes here, this fluid will come and rotate like this here. Now till this point you can analyze as if like it is the potential flow, right? So till this point only the potential flow. And here non-potential flow. And this is named as vortex flow. So that's why in our syllabus, if you notice, so potential flow is a separate topic and vortex flow is a separate topic. But in general, any fluid flow you can think of, it will always be coming together, not separately. But in our normal analysis, the theoretical analysis part, so we will be dealing the potential flow separately and vortex flow separately. But in practical, when we are dealing with as if like you are an engineer, then you have to take the complex level here. The potential flow and the vortex flow comes together. You have to analyze that. Got it or not? So here del cross F equal to 0, and here del cross F not equal to 0. So as del cross F equal to 0, then F is equal to minus del phi. But here you have to use other concepts which are related to vortex flow. That is a little bit complex. Here we are going to use the complex analysis. We are using the complex analysis. We will try to convert into the form of the potential flow to some extent. Got it? So these are the fundamental concepts that you have to be aware before we start this kinematics. Got it? Any questions? Any questions on this? Okay, so with this I'd like to stop the class for today. Tomorrow I'm going to solve some of the problems, and then I'll try to continue with, that is, the boundary conditions and the continuity equations. So tomorrow I'm going to deal with the boundary conditions and the continuity equation, and I will try to solve some of the problems based on the streamlines. Yeah, so till then, good morning. Yeah, bye bye.